real numbers. In this module, at first we will introduce real numbers. Then we will discuss the following concepts. These concepts are Euclid's division lemma and algorithm, the fundamental theorem of arithmetic, irrational numbers, rational numbers, terminating decimals, non-terminating repeating decimals. And finally, at the end, we will summarize all the concepts discussed in this module.
Let us recall the set of real numbers. This set contains the set of rational and irrational numbers. We know that rational numbers are integers, fractions, terminating decimals, and repeating decimals. Irrational numbers are non-terminating and non-repeating decimals. In this module, we will learn about the Euclid's division lemma. Let us first recall what we get when we divide 17 by 5. We get 3 as a quotient and 2 as a remainder. We can write it as 17 is equal to 5 multiplied by 3 plus 2. Similarly, we can show 17 is equal to 6 multiplied by 2 plus 5 and 20 is equal to 4 multiplied by 5 plus 0. Observe that in all the above cases, we have a positive integer a and another positive integer b, which divides the integer a and leaves a remainder r. Here we observe that r is always less than b. We can write the following expression. We will now define the Euclid's division lemma.
For given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, where r is equal to 0 or positive integer less than b. Now try to answer the following question. According to Euclid's division lemma, for a given positive pair a, b of positive integers, we have unique integers q and r satisfying a is equal to bq plus r, where r is equal to 0 or positive integer less than b. Now for a given pair of integers 40 and 3, find the pair qr. The options are as follows. To understand the concept of Euclid's division lemma, let us work out an example. Show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Solution. Suppose a is any positive integer and b is 2. Then by Euclid's division lemma, there exist integers q and r such that a is equal to 2q plus r, where r is equal to 0 or positive integer less than 2. Since r is an integer, so we get r is equal to 0 or r is equal to 1. Therefore, a is equal to 2q or 2q plus 1. If a is equal to 2q, then a is an even integer. We know that an integer can be either even or odd. Therefore, any odd integer is of the form 2q plus 1. An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Euclid's division algorithm is a technique to compute the highest common factor, HCF, of two given positive integers. HCF of two positive integers, a and b, is the largest positive integer d, which divides both a and b.
Let us now do an activity based on the division algorithm. Our objective is to find the HCF of 12 and 9. For this, we need two straws of different colors, a pair of scissors, and a ruler. Let us now do the activity. First, we will take two straws, one blue straw and one green straw. Now, we cut a 12 centimeter section from the blue straw and a 9 centimeter. Now, we cut a 12 centimeter section from the blue straw Now, we put the shorter straw, which is green, alongside the longer straw, which is blue. We cut the extra portion of the blue straw, which is 3 centimeters. Now, both the straws are equal in length. Now, we take the remainder section of the blue straw, which is 3 centimeters in length, and put it alongside the green straw. We cut the extra portion of the green straw. We repeat the same until the remainder portions of both the straws become equal. Now, we see that the length of the equal sections so obtained is 3 centimeters each. Hence, we conclude that the HCF of 12 and 9 is 3.
Now let us state Euclid's division algorithm clearly. To obtain the HCF of two positive integers, say c and d, with c greater than d, we can use the following steps. Step 1. Apply Euclid division lemma to c and d. We will find the whole numbers q and r such that c is equal to dq plus r, where r is greater than or equal to 0 but less than d. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at that stage will be the required HCF. Now, to understand Euclid's division algorithm, let us work out an example. Use Euclid's algorithm to find the HCF of 42 and 455. Solution: 455 is greater than 42. So we divide 455 by 42. We get 10 as a quotient and 35 as a remainder. Then by Euclid's division lemma, we get 455 is equal to 42 into 10 plus 35. Since the remainder is not equal to 0, we apply the division lemma to 42 and 35 to get 42 is equal to 35 into 1 plus 7. Now consider the divisor 35 and the remainder 7 and apply the division lemma to get 35 is equal to 7 into 5 plus 0. Here we observe that the remainder has become 0. So we cannot proceed further. Since the divisor at this stage is 7, the HCF of 455 and 42 is 7. Now let us work out another example. Find the HCF of 49 and 56 using Euclid's division algorithm. Solution: since 56 is greater than 49, we apply the division lemma to 56 and 49 to get 56 as 49 into 1 plus 7. Since the remainder is not equal to 0, we apply the division lemma to 49 and 7 to get 49 as 7 into 7 plus 0. Here we observe that the remainder has become 0. So we cannot proceed further. Since the divisor at this stage is 7, the HCF of 49 and 56 is 7.
The fundamental theorem of arithmetic says that every composite number can be written as a product of primes. Such factorization of this composite number is unique, apart from the order in which the prime factors occur. For example, a composite number x can be written as the product of primes in the following way, where a, b, c, and so on are the prime numbers and p, q, r, and so on are the order of their repetition.
Now try to answer the following question. Which one of the following is the prime factorization of 72? The options are as follows. Solution: 72 can be factorized as follows. Thus, 72 is equal to 2 into 2 into 2 into 3 into 3. Here we observe the factorization of 72 is unique, apart from the order in which the prime factors occur. Now let us work out another example. Prove that there is no natural number for which 4 to the power n ends with the digit 0. Solution: we have 4 to the power n is equal to 2 to the power 2n. This implies that the only prime factor of 4 to the power n is 2. Any number ending with 0 is divisible by 5. Hence, the prime factorization of the number must contain the prime 5. 5 does not occur in the prime factorization of 4 to the power n for any n. Thus, there is no number n for which 4 to the power n will end with 0. Now see an important result. Let a and b be two positive integers. Then we have HCF of a and b into LCM of a and b is equal to product of two numbers a and B. Let us work out an example. Find the HCF and LCM of 96 and 404 by the prime factorization method. Solution. The prime factorizations of 96 and 404 are as follows. Here we observe HCF is 2 to the power 2, that is 4, and LCM is 2 to the power 5 into 3 into 101, that is equal to 9696. Let us work out another example. An army contingent of 616 members has to march behind an army band of 32 members in a parade. 616 members has to march behind an army band of 32 members in a parade. The two groups have to march in the same number of columns. What is the maximum number of columns in which they can march? Solution. Maximum number of columns is equal to HCF of 616 and (32). By Euclid's division lemma, we get HCF of 616 and 32 as 8. Thus, the maximum number of columns in which two groups can march is equal to 8.
Irrational numbers. These are the numbers that cannot be expressed in the form of P upon Q, where P and Q are integers and Q is not equal to 0. Here are some examples of irrational numbers.
Now let us state a theorem whose proof is based on the fundamental theorem of arithmetic. Let P be a prime number and A be a positive integer. If P divides A square, then P divides A. Now we prove the theorem. Let the prime factorization of A be as follows, whereas P1, P2, P3 and so on up to Pn are primes, not necessarily distinct. We get A square is equal to P1 square into P2 square into P3 square and so on up to Pn square. It is given that P is prime and it divides A square. From the uniqueness of the fundamental theorem of arithmetic, it follows that the only prime factors of A square are P1, P2, P3 and so on till Pn. So P is 1 of P1, P2, P3 and so on till Pn. Since A is equal to P1, P2, P3 and so on till Pn, P divides A. There is another theorem under root 2 is irrational. Let us prove this theorem. Let under root 2 is equal to a upon b, where a and b are co-prime. From this expression we get b square is equal to a square upon 2. Therefore, a square is divisible by 2, and so a is divisible by 2. On substituting a is equal to 2m in b square is equal to a square upon 2, we get b square equals 4m square upon 2, or b square upon 2 is equal to m square. Therefore, b square is divisible by 2. And so b is divisible by 2. Here we observe denominator is power of 5 and decimal representation is terminating. Denominator is a product of power of 2 and 5 and decimal representation is terminating. Denominator contains 3 and 7 besides 2 and 5 and decimal representation is non-terminating repeating. Denominator contains a factor 3 square other than 2 and 5 and decimal representation is non-terminating repeating. Thus we see, in terminating decimals, denominator is a product of powers of 2 or 5 or both, and in non-terminating decimals, denominator is not a product of only powers of 2 or 5 or both.
Let x be any rational number whose decimal expansion terminates. Then, x can be expressed in the form p upon q, where p and q are co-primes. The prime factorization of q is of the form 2 raised to the power m multiplied by 5 raised to the power n, where m and n are non-negative integers. Consider the following example. Let x be any rational number such that prime factorization of q is not of the form 2 raised to the power m multiplied by 5 raised to the power n, where m and n are non-negative integers. Then, x has a decimal expansion which is non-terminating repeating. Consider the following example. .
Consider the following examples of rational numbers. Here we observe that the denominators of the decimal expansions are in powers of 10, which further can be expressed in power of its prime factors, that is 2 and 5. Observe the following examples of terminating decimals. In order to express a fraction p upon q in decimal form, we divide p by q. If after a finite number of steps no remainder is left, then we call it a terminating decimal. Observe some more examples of terminating decimals. Observe these fractions. We find a fraction is a terminating decimal only when prime factors of its denominator are 2 and 5. Let us work out an example. Which of the following fractions are terminating decimals? Solution. 1001 upon 4096 can be expressed as a terminating decimal as the prime factors of its denominator consist only of powers of 2. 1 upon 875 cannot be expressed as a terminating decimal as the prime factors of its denominator consists of powers of 5 and 7. (51 upon 300 can be expressed as a terminating decimal as prime factors of its denominator consists of powers of 2 and 5. 117 upon 3125 can be expressed as a terminating decimal as its denominator has only powers of 5 as prime factors. Let us consider following examples of non-terminating and repeating decimals. A decimal in which a digit or a set of digits repeats continually is called a repeating or a recurring or a periodic or a circulating decimal. Let us work out an example. Find the decimal representation of 8 upon 3. Solution. On dividing 8 by 3, we find that the decimal representation is non-terminating and repeating. Categorize the following numbers as rational and irrational.
In this module, we have learnt the Euclid's division lemma, which states that for any two given positive integers a and b, there exist unique integers q and r that satisfy the relation as shown, where r is always greater than or equal to 0 and less than b. We have also learnt about the Euclid's division algorithm, which is a technique to find the HCF of two given positive integers. Applying the Euclid's division lemma, HCF of two positive integers a and b with a greater than b can be obtained as follows. Find q and r such that a is equal to bq plus r, where r is greater than equal to 0 and less than b. If r is equal to 0, then b is the HCF. If r is not equal to 0, then we apply the same procedure to b and r until the remainder is 0. At this stage, the divisor will be the HCF of a and b. We have also learned about the fundamental theorem of arithmetic, which says that every composite number can be expressed as a product of primes. Such factorization of this composite number is unique. Mathematically, it can be represented in the following way. We have also learnt about terminating decimal expansion. If the denominator of a rational number is of the form of 2 raised to the power m multiplied by 5 raised to the power n, where m and n are non-negative integers, then the decimal expansion of a rational number is terminating. We have also learnt about non-terminating decimal expansion. If the denominator of a rational number is not of the form of 2 raised to the power m multiplied by 5 raised to the power n, then the decimal expansion of a rational number is non-terminating.
Let us go through the history of negative numbers. Let us see another real-life example of rational numbers.